So, of course, I want to introduce tonight's speaker, who is Mike Weber. Mike is a popular returning speaker for the museum, and he has a long history and love of Cornwall. As a child, he collected rock and mineral specimens from in and around the mine's waste rock piles, and that led him to the study of geology. As a 1982 geoscience graduate from Penn State University, Mike worked for 36 years as a geologist, health physicist, and manager for the U.S. Nuclear Regulatory Commission and the U.S. Geological Survey. After retiring from federal service, he returned to Cornwall, where he serves as a guide and researches the history of mining and the geology of Cornwall and similar deposits in Pennsylvania. So Mike is a weekly volunteer at the museum and gives guided tours of Cornwall Iron Furnace on most Fridays. So if you really like what you hear here tonight, you want to talk to Mike further, come over and book a tour with us on a Friday. He's also the author of a book that's coming out, Always More Production, and that will be a history of the mining operation at Cornwall, and that's due to be released later this year. So please welcome our speaker, Mike Weber.
Thanks, Mike. That's one of the things we haven't had on our Zoom sessions for the last 3 years. Applause. Not that I welcome that, but it's certainly nice to hear. And it's great to see people with us tonight in an audience, as well as the people who are joining us on Zoom. You know, on Zoom, we have people who watch these programs from around the world. And this has really helped to increase our outreach and share some of our history here in Cornwall with people from around the world. So I'm not sure who all is listening tonight and who is watching, but we're glad you're here in the audience and also glad people are with us on Zoom. I want to welcome you to this first of a series of fascinating and exciting programs. This is the first one for 2023, so it's great to also have you here tonight for this presentation entitled All About Slag. Now, having said that, I must say that I admire your courage and fortitude for participating in this presentation on slag. Many people might be reluctant to tune into a topic about slag. By the end of the webinar, however, I hope that you share some of my enthusiasm for this fascinating and absolutely necessary material in our society. I would like to thank the Friends of the Cornwall Furnace for participating and supporting this webinar. And I'd also like to especially thank Mike Emery, who just introduced me. Mike's the site administrator over at Cornwall Furnace. Kathy Donaldson, who's back there on one of the computers, and then Bruce Chadbourne, is waving his hand. Bruce is a resident here. If you have any computer questions, Bruce might be the person to go to. And he's also helping to video our webinar this evening. So, what is the big deal about slag? Well, slag is one of those important but little appreciated materials. During the tours that we conduct at the Cornwall Furnace, for example, we pay rather little attention to slag. In the tours that I conduct, I talk about slag in the beginning of the tour and explain where it comes from and what it's made out of. And then I point it out again when we're in the casting room of the furnace, where the slag came out of the furnace. However, many of us today might be quick to dismiss the importance of slag and overlook its complexity and the secrets that are contained within it. For hundreds of years, people have looked down on slag as a waste material from iron blast furnaces and from other furnaces. However, for the founders and the furnace workers that operated these furnaces, slag played a key role in helping them to produce quality cast iron. As Robert Forsyth stated in his book on blast furnaces in 1909, quote, "The proper mental attitude toward a slag is to consider it a reagent divinely appointed for the purification of metals." Now that's saying something. So after this brief introduction, I plan to dive into slag, figuratively, not really, including providing the answers to questions like what is slag, how is it produced, why is it necessary, what is slag made of, what can slag tell us about the furnace, what are its characteristics, what are the different colors. We already got into that a little bit in our questions before the presentation. How is slag disposed of? Can it be used? And where can slag be found around Cornwall today? Now, I do plan to leave plenty of time at the end of my presentation to answer your questions and also to listen to your comments. I also plan to heed the advice of my wife, Jane, and that is keep the presentation at a fairly high level, Mike. Don't get into too many technical details. My objective is to provide you with working knowledge so that the next time you go to Cornwall Furnace or to other blast furnaces, you know a little bit more about the slag and can better appreciate what you might be looking at. I'll also limit my presentation to discussing iron blast furnace slags. Slags are produced with many refining processes involving metals. I'm not going to get into those other metals. While there are some similarities, there's also some significant differences. And besides, if we just talk about iron blast furnace slags, we'll have more than enough material for our presentation this evening. So let's begin with what is slag? Well, according to the American Society of Testing Methods, one of the US standards organizations, slag is the non-metallic product developed simultaneously with iron in a blast furnace. Okay, what does that mean? In other words, slag is the solid material other than the iron that comes out of the furnace. Whatever solids need to be removed from the furnace, if they don't come out of the furnace in the iron, they have to come out of the furnace in the slag. Although the slag contains impurities that are present in the iron ore, the slag actually helps to remove those impurities that are naturally present in the iron ore and get them out of the furnace so they don't come out with the iron and they don't go up the stack with the gases. The photo on this slide, which you see, shows about 40 to 60 layers of slag that accumulated over time. Some of you might be familiar with this. This is pretty close to Cornwall Manor. If the slag was deposited in this location twice a day, you're looking at about 1 month's worth of slag that accumulated at this location in this 20-foot thick section of slag. So just to review, here's a cross-section of a typical blast iron blast furnace. And I'm talking tonight primarily about those furnaces that operated in and around Cornwall. So from a date perspective, we're talking about furnaces that operated from about 1740 until the early 1900s. At Cornwall Iron Furnace, the iron ore, charcoal, and limestone were dumped as solid materials in through the charging hole in the top of the furnace. The charcoal was the fuel, and it burned primarily at the bottom of the furnace where air was injected into the furnace. The gases from the burning charcoal and also from the limestone and ore went up the stack and exited out of the top. As the solid limestone and iron ore descended deeper into the furnace, they eventually melted. And then the iron was tapped or discharged at the bottom of the furnace, where the slag was also removed from the furnace. Now, before we leave this slide, I wanted to highlight two interesting factoids about the operation of these kinds of furnaces. So the first one is that air injected at the base of the furnace travels as far upwards in 1 second as all the descending solids move downward in 1 hour. I'll repeat that. The air injected at the bottom of the furnace moves as far upwards in 1 second as all the solid materials dumped in the top of the furnace descend in 1 hour. It's kind of mind-blowing when you think about that. And the second one is also pretty astounding. The weight of air. We don't usually think of air as being rather heavy, right? The weight of the air consumed in the furnace per ton of iron produced is about twice that of the weight of all the solid materials that are entered into the furnace. The weight of air consumed in the furnace per ton of cast iron produced from that furnace is about twice that of all the solid materials, the charcoal, the iron ore, the limestone dumped into the furnace. That's pretty astounding. That's a lot of air, and it also tells us a lot about what's going on in the furnace, what kind of processes are going on, and some of the dynamic movement of materials, the air, the charcoal, the iron ore, and the limestone. So in tapping the furnace, when a furnace is tapped, the slag is removed first because the slag is less dense than the iron that is more dense underneath. So in the early furnaces, the slag was directed to gutters and then allowed to flow out onto the sand in the casting room where it cooled. You can see in this picture like a hot liquid slag flowing out of a furnace and then collecting in a rail car that was designed to transport that slag away from the furnace. You can also see in the background there, those horizontal layers. That is also slag that was previously tapped from the furnace, has become like rock and is sitting there behind the ladle that's picking up the slag. Now, after the slag was removed from the furnace, then the founder would tap the liquid iron and use that to cast pig iron or other cast iron items like hollowware, for example. So in this cartoon diagram, we can talk about how slag was produced. You notice that blob up in the upper left-hand corner. That simulates or symbolizes the iron ore. So you have iron, that's the Fe in there, and then you have impurities. The little green lettering signifies the impurities. Most of that iron is present as iron oxide, or iron atoms that are chemically bonded to oxygen atoms. To produce iron from the furnace, you have to separate the iron from the oxygen atoms. And that's where the second ingredient, limestone, comes in. From the melting of the limestone and the burning of the charcoal, you can reduce the iron, taking it back to its native state. And that produces iron metal, which after all is the product that's sought from a furnace. And then the impurities that were originally present in the iron ore become more attracted to the limestone than they are to the iron metal. So they leave the furnace in the form of the slag, which you see in this lower right-hand corner. I should point out that in some furnaces, they didn't use limestone. They used things like clam shells and oyster shells, or they may have used other rocks that were naturally rich in calcium. But here in central Pennsylvania in the Lebanon Valley, we are blessed with lots of limestone. So you didn't need to use any substitutes in the furnaces around here. You had plenty of limestone to feed into them in the Cornwall, Lebanon area. Well, why is slag necessary? Ancient Chinese civilizations figured out 1,000 years before the Common Era, or about 3,000 years ago, that by adding limestone into the furnace, along with the charcoal and the iron ore, they were able to separate out the iron from the ore and remove the impurities. The molten limestone removed those impurities and kept them from clogging up the furnace. In addition, sometimes other impurities come along with the slag. For example, coal, like anthracite or bituminous coal, or coke might come along out, or charcoal might come along out with a slag. You might have solid pieces of iron ore and limestone that don't quite melt in the furnace. They'll come along out with a slag. Sometimes ash residue from the combustion of the fuel will come out in the slag. And then sometimes even the lining of the furnace comes out along with the slag. It's not desirable, but nevertheless it happens. In fact, sometimes you even find pieces of cast iron in the slag that escapes the casting process and comes out with the slag. So when you're walking around looking at slag, sometimes you can see pieces of iron. And I have some samples of slag which you're welcome to come up and look at after the presentation. We can talk more about what you're looking at. And I had a gentleman donate some slag from the North Cornwall Furnace just before the talk. So we certainly appreciate that. Well, with all that discussion about slag, what is it made of? Because of how the slag forms in the furnace, slag has a wide range of properties and compositions. The composition of the slag will vary as a function of what materials are added into the furnace, the limestone or the flux, the iron ore, the fuel, the proportions of those materials, the quality of iron that's produced in the furnace, and how the furnace is operated. So that composition, you might well imagine, will vary a lot. Slag compositions, in fact, can vary from cast to cast using the same solid materials being added to the furnace. And sometimes even within a single cast, the slag composition can vary in the same furnace. So most of the slag is comprised of 4 oxides. You see them listed there. First one is silicon dioxide, otherwise known as silica. Alumina trioxide, which is aluminum trioxide, which is alumina. Calcium oxide, which you know as lime. And magnesia, which is magnesium oxide. Those are the 4 principal oxides. And then along with those come some other materials. Now, extensive analyses of slag from blast furnaces in the United States in the 20th century give us this range of compositions. So the silica, you can see, varies between about 33 and 42%. The alumina between 10 and 16%. The lime, 36 to 45%, almost like the silica. And then the magnesia, 3 to 12%. And then those other components such as sulfur, 1 to 3%. We were talking about breaking the slag beforehand and how you could still smell the sulfur from the slag. Iron oxide up to 2%, and manganese oxide up to about 1.5%. Okay. I'm being told that we're closed captioning. Okay. Sorry about that. Another one of those discoveries. Now, to illustrate better the typical slag from Cornwall, I put on this slide the composition of a piece of slag that probably came from the Bird-Coleman furnaces. The Bird-Coleman furnaces right here in Cornwall used limestone from Cornwall as well as the iron ore from Cornwall. And the fuel that they used was anthracite coal. And you can see that the silica content of this slag is about 34%, the alumina content about 15%. And so the ratio of silica to alumina is 2.3, and that's about typical for an iron blast furnace slag. You can see some of that slag over on the right-hand part of your screen from the Bird-Coleman furnace. So early scientists in the 18th and 19th centuries, when Cornwall Furnace was starting to fire up, had a difficult time characterizing the composition of the slag for a couple of reasons. One was the primitive state of chemistry as a science back then. And another was this complex relationship between the various components of the slag. For example, if the amount of lime increased, then the amount of alumina or silica would have to decrease proportionately. By the early 20th century, scientists learned that they could chart these more complex relationships by using diagrams like this one, which is called a ternary diagram, where you're plotting the composition against 3 different axes. In the lower left-hand corner, that's 100% lime, calcium oxide. Lower right-hand corner is 100% aluminum trioxide. And then on the vertex of the triangle, you have 100% silica. If you had a material that was made up of equal amounts by weight of lime, silica, and alumina, it would plot in about the middle of that triangle. I highlighted on this triangle in the orange the range of most blast furnace slags. And you can see there that the ratio between silica and alumina is about 3:1 by weight. And the amounts of silica added to alumina equals about that of lime and magnesium. Now, if the slag contained too much lime, which you see in that lower left-hand corner of the triangle, say, for example, more than 50% lime, then the slag slakes when it comes out of the furnace. It decomposes rapidly into a white powder when it's exposed to the outside elements. And that, like I said, is on the triangle down there in the lower left-hand corner. Another way to depict the composition of slags is to examine the minerals that are contained in the slag. The chemicals combine to produce a variety of minerals. Because slag is made by humans and minerals are by definition naturally occurring, some geologists would say, oh no, don't talk about the minerals of slag. Nevertheless, for our purposes here tonight, we can describe slag in terms of the minerals that comprise the slag. And I show on this slide pictures of the crystals of those minerals that typically make up slag. You're not going to see nice crystals like this typically in the slag. So I thought I'd show you what they really look like if they were present in their pure state. So you have minerals like melolite, olivine, pyroxene, merwenite, and then pseudoelastonite. Geologists, mineralogists love big words like that. The formation of the crystals of these minerals is a function of the composition of the slag and also how rapidly the slag cools once it's removed from the furnace. It starts to crystallize. If the slag cools quickly, which it most often does, then there's not enough time for the crystals to form, and so you get very glassy slags. We were talking about that a little bit before the talk started tonight. Glass is non-crystalline, and so it's what's called amorphous. And but if you allow that slag to cool a little bit slower, then you can start to grow crystals once the temperature of the slag drops below 2,640 degrees Fahrenheit for most compositions of slag. And then if it cools even slower, well, those crystals can grow larger and new crystals can form, again, depending on the chill rate and the composition of the slags. But again, most slags cool faster, so they don't really grow large crystals. And slags from furnaces that are fueled using coal blast charcoal typically produce higher silica or more glassy slags, whereas hot blast furnaces that use coal or coke as the fuel typically don't produce those glassy slags. And that's exactly what we see in Cornwall, and we'll talk about that more later in the presentation. So now that we've talked about what slag contains, we can discuss the physical characteristics of the slag. As I previously stated, these characteristics can vary considerably, just like the composition. One of the most characteristic features of slag is the presence of gas bubbles or voids or vesicular cavities. The voids in the slag give it a higher porosity, even though those voids may not necessarily be interconnected. But because of those voids, the rock, the slag, is less dense than most rocks. So the average density, bulk density of slag is about 80 pounds per cubic foot. Now at Cornwall Furnace, the slag that it produced is about 160 pounds per cubic foot. Again, it reflects the differences in the composition and how the furnace is operated. In addition, other characteristics of slag, the slag tends to be highly durable. It's resistant to mechanical erosion. It can withstand high temperatures. It's relatively tough compared to other rocks, and it has a low thermal expansion. And the color of the slag can vary considerably. Most slags vary from light gray to dark gray. In contrast, some of the more vitreous slags, those slags like come out of a coal blast furnace, can take on a range of color depending on the impurities that may be present in those slags. For example, if you see a slag with that sky blue color, that may indicate elevated amounts of manganese present in that slag. And slags that are violet and purple might be colored because they have more manganese or nickel. Slags that are blue, green, and green have elevated levels of reduced iron or ferrous iron. And yellow, green, and brown slags suggest elevated levels of iron, manganese, or sulfur. Brown and black slags may indicate elevated levels of iron and graphite carbon. Sometimes some high quality slags that are brightly colored are very glassy and don't have very many bubbles in, can be cut, polished, and used in making jewelry. So some of those slags are highly sought after by collectors. So with that background, what can slag tell us about how the furnaces were operated? And why is slag so important? Well, for centuries, workers at hot blast iron furnaces described ideal slag as hot, fluid, and gray. In other words, when the slag was tapped from the furnace, ideal slag flowed rapidly out of the furnace without froth or high viscosity and turned light gray when it solidified. The observation that the slag flows freely and rapidly means that the slag typically contains lower amounts of silica. The slag that contains too much silica would not melt properly in a furnace. So that would create other problems in the operation of the furnace. The characteristics of slag in the furnace were told the furnace workers about the composition of the slag and also the temperature at which the furnaces were operated. In the 18th and 19th century, without detailed chemical or physical ways to measure these things, the furnace workers had to rely on what they could physically observe in terms of the characteristic of the iron and the slag. And that gave rise to two primary variables that the furnace workers tried to control in operating the furnace. First, the temperature at the bottom of the furnace when the air was blown in and the slag and the liquid iron accumulated. And secondly, the proportion of limestone or the flux that was added in comparison to the iron ore and the fuel that was added into the furnace. The relative temperature was more important to these furnace workers than the absolute temperature, because that was something that they could control better. They gauged the relative temperature by looking through a peephole near an air inlet or a tuer. And the slag temperature looking through there was estimated based on its color and its fluidity. Now, I don't know if you've ever seen inside of a hot blast furnace, but there's a lot of light that's streaming out of that little peephole. And so I admire the furnace workers for their ability to discern one kind of slag compared to another. They also looked at the characteristics when the slag and the iron were tapped from the furnace. For example, did the slag flow out rapidly or was it sticky and viscous? Did the iron emit sparks when it came out? Or was there scum seen on the surface of the iron when it was tapped from the furnace? All these were indications to the furnace workers about the relative temperature and the composition that was happening inside the furnace. So the furnace workers, and this is a key point, learned that to make high-grade cast iron, they first needed to make high-grade, high-quality slag. Gray slag generally indicated that the iron produced in the furnace was high grade and contained a little bit of carbon in the form of graphite. Darker gray and black slag, on the other hand, suggested that the iron was lower grade and contained less graphite carbon. So how much slag was generated by these furnaces? Well, as in most of the answers in my presentation so far this evening, you already got this recurring theme. It depends. It depended on a variety of parameters. In general, and we always have to watch generalities, but in general, about 1/2 to 1 ton of slag was generated for every ton of cast iron produced. So at the Cornwall Furnace, which generally produced about 3 tons of cast iron a day and operated nominally about 9 months out of the year, Cornwall Furnace would have generated between 400 and 800 tons of slag a year. The anthracite, Burn Coleman, and North Cornwall furnaces were much larger, so they would have generated much larger quantities of slag. So, for example, in 1880, Cornwall Furnace produced 675 tons of cast iron. That was 3 years before the furnace closed. So that was about the peak of their production. In contrast, Berg-Coleman furnaces, and there were 2 of them, produced about 10,500 tons of cast iron a year. If we use those amounts as representative for the furnace production of iron, that means that the Cornwall furnace would have generated between 48,000 and 95,000 tons of slag during its 141 years of operation. In contrast, Berg-Coleman furnaces would have generated between 200 and 400,000 tons of slag during their much shorter lifetimes. If you convert those tons of slag into a volume, and you account for the differences in the furnace and the compositions of the slag, Cornwall furnace produced about 600,000 cubic feet of slag, and the Berg-Coleman furnaces produced about 10 million cubic feet. That's a lot of slag. So how did the furnaces dispose of all this slag? Well, in the early years of furnace operation, most of the slag generated by the furnace was disposed of relatively close to the furnace. You can see on this slide, on the left-hand side, an illustration of the Cornwall furnace from about 1800. And you see that white pile there, which I've labeled in red letters slag. I added the slag, but the rest of that illustration is untouched from how it was produced in 1800. After the slag was tapped from the furnace, it was allowed to cool on the sand in the casting room floor, and then it was broken up, loaded onto wheelbarrows, and taken outside and dumped in that slag pile. Today, that slag pile you can see in the right picture, and it's covered by soil and vegetation. So it doesn't look much like slag anymore, but we're pretty sure that it's there. We're going to try to verify that in the not too distant future, but every indication is that the slag is there underneath that pile. In the middle picture, you see a piece of slag from the Cornwall furnace. And I have that piece up here if you want to look at it after the talk. First of all, notice how glassy it is. So again, that's pretty typical for a coal blast charcoal fueled furnace, that the slag is more glassy. Second, note the rind that's on the bottom of the slag, which is actually on the top of this picture, just to illustrate it. You can see, if you look closely at that slag, where it cooled, sitting on top of the sand. And then on the very top, you can see how glassy it is. It's because the slag on the top in the air would have cooled much faster than it would have cooled on the contact with the sand. And so on the bottom rind of that piece of slag, you can actually see little crystals of those minerals that we talked about before, because they had more time to grow in that piece of slag than they did at the top of the piece of slag. You can also see how those gas bubbles were trapped by the very glassy slag. Now, in later furnaces, particularly the hot blast furnaces that were larger and produced greater quantities of slag, the slag was tapped in its hot liquid form, and it was flowed into large ladles that were then either lifted by overhead cranes or were carried in special rail cars away from the furnace, where they were then dumped. Because the slag was dumped as a hot liquid, it would flow across the ground surface and find the lowest elevation, such as a creek channel. As noted by the U.S. Bureau of Mines, and this is a quote out of one of the publications I have up here, quote, "One of the most striking features of an iron and steel plant is the mountainous bank of slag that presents a continuous pyrotechnic display as ladle after ladle pours its incandescent load down in an endless accumulation of a waste product," end quote. That's a sentence. Over time, the surface around the dumping locations would slowly build up as layer after layer of liquid slag was poured across the surface, and then the slag piles grew. In the upper right-hand corner of this slide, you see a picture of the Robisonia furnaces, and they were still, or furnace when it was still operating. You could see smoke coming out of the stack, and you can also see them dumping slag along short rail spurs that proceeded out of the furnace building. And so those rail spurs were elevated, and so when they dumped, that slag would flow away from the rail spur and create these large slag mounds. And the bottom picture, you can see in the foreground, 2- and 3-story houses that are dwarfed by the size of those slag mounds. So that gives you a good understanding of the amount of slag generated and how these later furnaces took care of that slag. And of course, the ore for the Robisonia furnace came from Cornwall. So with all that slag, can it be used for some productive applications? Well, the answer to that is yes. Although the furnace workers considered the slag a waste, the slag could be used for beneficial applications. Even at Cornwall Furnace, even though we think most of the slag is present in that pile next to the furnace building, some of that slag was used as fill in the low-lying areas surrounding the furnace. By the 1940s, countries around the globe were actively using their slag, generating about 66 million tons a year. And in that same year in the United States, about 60% of the slag that was generated was being used for beneficial applications. Now, historically, slag has been used for a whole variety of applications. I only list some here. For example, in Germany in 1589, they used slag to make cannonballs. That didn't work so well. They also cut slag blocks and used them in construction in Europe in the early 18th century. Slag has been used as a railroad ballast or as the roadbed for railroads since about 1875. And in the 19th century, slag has been used for concrete and also cement, both in Germany and in the United States. For example, the Harrison Estate Building in Philadelphia was constructed in 1897, and as a demonstration project, they used slag and reinforced concrete to construct that building. The suitability of slag today for commercial use is a function of its physical characteristics and also its composition. In 2019, just 3 years ago, 4 years ago now, about 17 million tons of iron and steel slag were sold in the United States for $470 million because of the use of that slag in other applications. And in that same year, the USGS reports, US Geological Survey, that about 2.3 million tons of slag were imported to the United States from Japan, Canada, Brazil, and Italy to use that slag for its beneficial purposes. Around the world, about 440 million tons of slag are generated now each year from both iron and steel furnaces. And that slag is used for construction fill, for road construction, concrete and cement manufacturing, and used as filter media. A small amount of slag is even used in producing slag glass. Some of you may be familiar with slag glass. Slag glass, you can see in that picture in the lower right-hand corner, it's that marbleized colored glass in the lampshade. That's slag glass. So where can slag be found today around Cornwall? Well, because of the amounts of slag generated in Cornwall, slag can be found all over the place. Besides the relatively small pile that I already showed you next to the Cornwall furnace, slag can be found near and around the other blast furnaces that operated in Cornwall, including Anthracite Furnace, Coleman Furnaces, and the North Cornwall Furnace. Some of the slag has been removed and used for other beneficial purposes, such as road construction and railroad construction. And you can also find slag from the Coleman furnaces along the Lebanon Valley Rail Trail, especially just to the southwest of the Iron Truss Bridge here in Cornwall Center. Now, using a little bit of geologic detective work, you can even see the remaining piles of slag near those furnaces using remote sensing tools. It's difficult in the picture on the left, which is of Cornwall, you see the open pit there, to see these slag piles. However, that's an aerial photograph. If you use a laser imaging detection and ranging image, otherwise known as a LiDAR image, you can see remaining piles of slag near each of the blast furnaces in Cornwall. And I've circled them in red, so you can see Cornwall Furnace is the smallest, and then you see Bird-Coleman furnaces and also the piles near Anthracite Furnace. In addition, I marked the Lebanon Valley Rail Trail in red so that you can go along there and find the slag where it was used as ballast. LiDAR imagery is especially good in highlighting steep side slopes. And you remember seeing how the slag was disposed of, that creates these typical steep side slopes. And that's why LiDAR imaging is so effective. Now, having shown you these maps, let me remind you that most of the slag today remains on private property. So if you're tempted to go exploring the slag piles, you will need to make prior arrangements with the property owners. And in addition, the slag at the Cornwall Furnace is on land that's owned by the Commonwealth of Pennsylvania and managed by the Pennsylvania Historical and Museum Commission. That means that any slag on that land is state property and is protected accordingly. You're welcome to admire the slag, but the slag is what you might call leverite. Leave it right where you found it, because we want to preserve it for existing and future residents of the state. And one more brief mention about this topic, archaeometallurgy. Because of all the slag that's generated by iron blast furnaces, and because of the durability of that slag, you can even use studies of slag to do a little bit of archaeology, as we see here. The furnaces and the iron products that they produce may be long gone, but all these piles of slag tend to kind of stay around close to the furnaces. So you can analyze the piles of slag that, by using the iron carbon phase diagram you see on the left-hand side of the picture, and also on the right-hand side of the picture, you see a micro photograph of wrought iron, and in that wrought iron you can see those dark gray blebs of slag, and that's a function of how that metal was prepared. So by using some of these archaeometallurgical tools, you can actually supplement and better understand the history of some of these iron production facilities. So that brings us back to where we began this talk, with the recognition of the divine appointment of slag for the purification of metals, including iron. I want to thank you for your attention throughout this presentation. I also hope that you now have a deeper appreciation and you're more enthusiastic than ever about slag. And I, of course, would like to thank the Cornwall Iron Furnace Associates for sponsoring this webinar, especially Mike Emery, Cornwall Site Administrator, Kathy Donald back there, who's our treasurer for the Cornwall Furnace Associates, Kathy Donaldson, and Bruce Chadbourne, who's the Cornwall Manor resident and our videographer and technical engineer for our session tonight. And now, after Mike takes over, I'd be happy to answer your questions and listen to your comments. Thanks.
Actually, what we're going to do is I'm going to start with just a few of our questions online. And then after we start with that, we'd like to take a few more of your questions. Also, if you would be willing to support this evening's talk tonight, we are going to pass a basket around. If you're able and inclined and like what you heard, we'd love the donation. You know, if you're not able to tonight, no hard feelings. We're glad you came out and were able to do this. So let me go ahead. I'm going to sit down here in the front so I could say these to you. That'll be a little easier.
All right.
And then have it. So
You might want to answer them too.
I might. They want to hear your answer. So first question. What are some of the long-term effects of slag piles on the surrounding environment?
Of course, like many of the other answers. So the question is, what are the long-term effects of slag on the environment? That answer is going to be a function of the composition and also the characteristics of the slag. Some of the slags that I've already described their characteristics, they're very durable, and so they're relatively stable in the environment, and they don't really cause any concerns. Other slags might contain trace metals and other constituents, which over time could leach out of the slags and cause some environmental concerns with local contamination. But the vast majority of the slags, especially those that were studied throughout the 20th century, suggest that that slag is relatively stable. So they really don't pose that much of an environmental danger.
So this is another good question. Where did the word slag itself originate?
So the question was, where did slag originate? And there's a variety of answers to that question. The one that I'm familiar with is it came out of one of the things I did not talk about tonight were bloomery forges. So in bloomery forges, instead of melting the metal, you heated up the iron ore and then you pulled it out of the hearth as a bloom, and you pounded that bloom over and over again. Through repeated heating and pounding of the ore, you drove off some of these impurities that were part of the iron ore, and that's the derivation of the term slag. It came from, I think, the German word for the dross, or the material that you would drive out of the iron that would become the slag. And then the slag from the blast furnaces is also very similar to the slag that's produced from the bloomery forges. Although it's a lot more work in the bloomery forges.
So another question is, of course, any known uses of slag around Lebanon and in buildings?
I don't have specifics. The question was, do I know any uses in particular of slag in the Lebanon area, and including use in buildings? So, like I said, I don't have specifics. Given the amounts of slag generated both here in Cornwall and in Lebanon and in Rabazonia and in other nearby locations, I have no doubt that slag was used in constructing concrete in buildings, as well as in many roadways. One of the pictures I showed in my presentation was excavating slag from Bird Coleman. In my next presentation about the 1920s, I'll talk some more about that. But we know that slag, for example, in that time period, was removed from the slag piles here and was used in constructing roads as far as Mount Gretna and Schaeferstown and many other locations. So road construction, railroad ballast, concrete and cement fabrication, backfilling around sewer lines, slag has been used extensively.
Another question, because of the use of the word slag, Mike, is questions about the slag dams and the slag ponds that were across from Goostown.
Right.
Could you talk a little bit about that?
Yeah, so the question deals with the use of slag perhaps in a slightly different way, such as the slag dams or the slag ponds near Goostown. So because of the size of slag piles, many people grow up, especially in their early ages, and they think of any big pile of waste as being a slag pile. So sometimes that terminology gets then appropriated and applied in other settings. For example, above Rexmont, the tailings impoundment was constructed when the concentrator plant for Bethlehem Steel was built here between 1960 and 1962. I've heard a number of people refer to the tailings impoundment as a slag pond, but it never contained slag that I'm aware of. It contained finely ground ore that had been physically and chemically treated from the concentrator plant. Same thing in Lebanon off of Lehman Street. You had people referred to as the tailings impoundment there as another slag pile. It's a similar appropriation of language as we might use for dumps. You know, there are municipal waste landfills that people call dumps. There are people's homes that people call dumps. So it's often helpful for me in my guiding people through the furnace to remember the specific use of the terms and not to use some of those colloquial expressions. Does that answer your question? Okay.
Another question came in about the businesses that actually started to show up dealing with slag more in the 20th century.
Yeah, so the question was about businesses that showed up in the 20th century that processed slag, and indeed there are many of those businesses. As I stated in my presentation, in 2019, we had that large amount of slag that was produced and then sold. 21 million tons of slag in the United States from iron and steel mills. And then that was sold for $470 million. Now, the people who bought that slag were these companies whose business it is to process the slag and convert it into useful products. So, for example, they may grind it and they may make it into materials that can be added to concrete, for example, or cement. These are the middle companies. And so we're actually benefiting as a society from these companies because they're giving gainful employment to their employees. And they're also helping to reduce the amount of these slag piles that are sitting around in our communities and using that material for some beneficial application.
Just a couple more, Mike. Is slag still a byproduct of the modern steelmaking process, like electric arc furnaces and oxygen?
So the question is slag still a byproduct of the more modern furnaces, like electric arc furnaces and oxygen furnaces, basic oxygen furnaces? And the answer is yes, depending on what their feed materials are and how they're operating those furnaces. But like I mentioned in the talk, you still have 21 million tons of slag being generated, plus the slag being generated outside of the country being imported in the country. That slag is coming from modern steel and iron mills and furnaces.
So the question is, where was Cornwall Furnace in relation to the slag pit between the rail trail and Ironmaster Road?
So the question is, where was Coleman Furnace? And I go back to my 21st slide. You don't see where the furnace was located anymore. In part, that's because after the Coleman Furnace was torn down, they continued to apply waste rock from the mining operation in the open pit on top of where the furnace used to reside. But if I could use wake up my cursor, I don't know if you can see it, but it would have been located right about here. So just off the rail trail and to the northwest of the open pit. Okay, questions here?
Where is it on campus in relationship to that picture?
So, whoa, didn't mean to do that. So, come on, gotta wake up my cursor here. Here's the Cornwall Furnace. Buckingham campus is right here. And then of course, Cornwall Manor is much larger today than the original grounds of the Iron Masters estate, the Buckingham campus. So
Where the woods are?
ooh,
The woods part of
maybe Bruce can show you where the woods are.
See where the word bird furnace,
Right here,
that's the woods.
these are the woods.
Is it safe to assume that most of the soil on our campus has a pretty fair amount of slag?
Here at Buckingham campus,
Yeah.
no. Because those are the grounds of the Iron Masters estate. And they wanted to keep those grounds pristine. So there might be some, like along the roads, or they may have used some to backfill if they were putting in drainage lines, water lines, or sewer lines. But most of the grounds here, I think, would be relatively clear of slag. You might find, you know, one here or one there, but not anywhere near what you'd find if you dug into the slag piles that I highlighted on the LiDAR image. Other questions? What back here?
And we hear a lot about radon in Pennsylvania. Do you suspect that radon would be present in the slag piles that are, you know, here in our community?
Okay.
My home's actually built on North Cornwall Furnace slag pile.
Okay. So the question was, we hear a lot about radon in Pennsylvania, indeed all throughout the United States and around the world. Is slag a source of radon, or do I think it would be? And the answer is no. Because the ores, the limestone, and the fuel that was fed into the furnace typically were not rich in either the uranium or the radium, which are the precursors of radon. So in general, I think the answer would be no. Now, that's not to rule out the possibility that some particular type of limestone or dolomite may have been used as a flux, and that may have elevated radium in the limestone. So the best approach is to have your home tested.
That relates to actually one of the online questions about have toxins ever been found in slag depending on location of materials?
Yeah, so the question was, have toxins been found in slag? And the answer is yes. Depending on what materials were fed into the furnace and then how the furnace was operated. Sometimes if we're talking about heavy metal contamination in the slag, a lot of those heavy metals might go with the iron into the iron and then later into steel if the iron is used for steel. But it's a function of the chemistry and what's happening inside the furnace. And we chatted before the talk about sulfur and how sometimes when you strike a piece of slag, you can still smell sulfur, even though that slag may have been generated 150 years ago. Sometimes the sulfur would go into the iron in the furnace, and sometimes it would stay behind in the slag. And that's when you get into the detailed chemistry of what's happening in the furnace and how the furnace is being operated. So for the very same reasons, the movement of any particular heavy metals, like chromium or arsenic or something like that, that may have been present in the original ores, may or may not go into the slag depending on how the furnace is being operated and what other materials are being fed into the furnace. Yes?
I understand the slag floats on top of the metal, and when they draw the slag off, how do they know that they aren't getting into the good stuff?
Okay, so the question was understanding that the slag floated on top of the liquid metal, the iron, because the iron is more dense. How do they know when they're not getting into the good stuff? The simple answer to that question is because you see it flow out of the furnace. You can see the difference between the slag, which is first tapped, and then the iron, which comes along behind. So typically, if they were tapping the furnace to remove the slag and they started seeing liquid iron come out of that port, they would stop it and then they would start tapping the iron out of the furnace.
Can they stop it just like that?
The question is, can they stop it just like that? It's not so simple. But what they would do is they would drive in a sand and clay plug. And so with some finesse and experience doing that many times, they could do it a little faster than I might be able to do it.
I was wondering if you had a product that would fix slag in, iron.
Oh, yes. So the question is there a product where there's mixed slag and iron? Some of our samples that we have up here have iron mixed in with the slag, so you can see that. I'm not aware of any intentional mixing of slag and iron as a product, but I am aware that for many years, slag piles were mined to recover the iron that escaped in the slag. And it was actually a good way to feed a furnace because the iron had already melted and it had been somewhat purified, so it was a good source of iron. Stamp mills were built around many of these slag piles. We talked earlier about companies that were in the business of processing slag. So some of these companies built stamp mills like they used out west to produce gold ore, specifically to recover the iron from the slag.
Last one, other than measuring the weight of the air.
Oh, so the question is, how do they measure the weight of the air? So that is indeed a calculated amount. They knew how much air they were blowing into the furnace, and they knew how much iron they were getting out of the furnace. And so you could calculate the weight of the iron, the weight of the air that was being forced into the furnace in the blast. So they didn't actually weigh it. You could do it. Yes, sir.
Above, on your LiDAR photo, above the word Bird Pullman,
Yes.
there's a long skinny hill.
Yes.
Is that tailing?
No. So that is, it's called Midway Ridge, or it's a sedimentary unit, rock unit, which has more shale in it, so it's more resistant to erosion. And that's what creates that ridge just north of, well, this is north of Cornwall Center, I guess.
North of the wood.
Yes, it's on both sides. So it's here. That's not slag, but this is the slag from anthracite furnace. Good questions. Yes, sir. Whoa.
You made a distinction between coal something with a coal blast or coal fire.
Yes.
At first I thought you were saying coal.
Oh, okay. I'm sorry. I should have enunciated my D.
Okay, but what's the distinction?
So there's two basic types of furnaces that operated here in Cornwall. Cornwall Iron Furnace was a cold blast furnace. That meant that you could inject ambient air without heating it into the furnace because you were using charcoal as the fuel. And as long as you had enough air blowing into the furnace, that charcoal would continue to burn. In contrast to that, in a hot blast furnace, those furnaces used coal, C-O-A-L, or coke, C-O-K-E, which were fuels. But in a coal or coke fueled furnace, you had to preheat the air. So they're hot blast furnaces, and that was required to sustain the burning of the fuels. Good question. Thanks for asking that question. So if it wasn't clear, hopefully it's a little clearer. Other questions? Sir.
Can you point out what the bridge is? The railroad bridge?
I think so. Bruce might want to do that. I think it's right about
Above
There.
that middle ridge there.
above here. Come on, come on.
Right about, yeah, right about there.
Yeah.
Just a little bit further up, further.
Close to where the mill was.
Yeah.
Sometimes that ridge is called Millway or Mill Ridge, because the mill was there and everybody knew where the mill was, because that was the mill where all their ground grains were coming from. Yes.
two comments. One, in the late 40s and early 50s, we referred to the North Cornwall slag pile as a cinder bank. I guess there's a correlation there between slag and cinder.
Okay, so the comment was referring to a slag pile as a cinder bank. And is that the same as a slag pile? And the answer is yes, if you recognize that the slag pile contains more than just the cinder from the furnace. Normally cinder is the residue from the combustion of the fuel. So there is cinder that's generated in a furnace, and that cinder ends up in the slag. You often talk more about cinder banks when you're talking about refinery forges or chafing forges, because there you're using the coal and you're producing cinder, and that takes on the appearance of another kind of rock called scoria, which is a kind of volcanic rock, has lots of air bubbles in it. And then of course they would grind up the cinders and use that in on the road surfaces during the winter time, because that would give you more traction if you were trying to get around in your Studebaker. Did you have another comment?
Yes, on the North Cornwall.
Yes.
Slag, I've experienced with excavations there, and that was poured in a molten state as opposed to the cold state.
Correct.
Yeah.
Yeah, so the comment was at North Cornwall, the slag was deposited in a molten state, not in a cold state, and that is correct. Same with North Cornwall is what you're talking about. Same with Burke Coleman, and same with the anthracite furnaces. Of the 4 furnaces that I specifically talked about, other than Robisonia, only Cornwall is a coal blast furnace, charcoal fueled, and that's where the slag was allowed to cool, then broken up, and then taken out in solid form and dumped. Because of course the slag was in much smaller quantities, and it was more manageable for them to do that than the larger hot blast furnaces.
Can I mention that the slag was going off twice a day, noon and midnight?
Yes.
That's been a project to dump the molten slag in at midnight.
Yes. Now this gets back to the pyrotechnic and the incandescent glow. And so the comment was tapping the furnace twice a day. That must have been quite a show if they were pulling out slag at midnight. Some of those hot blast furnaces were actually tapped even more frequently, like 4 times a day, every 6 hours, depending on how they were operating the furnaces. So that's why the Bureau of Mines quote is especially meaningful, because if you've ever seen videos or you've seen actual dumping of slag, it is quite a sight. So if you're around an active steel mill or iron furnace and you have the chance, it's a spectacular sight. Other questions, comments? Well, you've been a very gracious audience. I appreciate both those of you here with us at Cornwall Manor, as well as those of you who have joined us on Zoom, and I'll turn it back to Mike Emery.
Well, again, thank you everyone for joining us tonight. And thank you for joining us for this lecture. Of course, I especially want to thank Mike Weber for his presentation, Kathy Donaldson and Bruce Chadbourne for helping to organize our virtual talk. Also want to thank the Friends of the Cornwall Iron Furnace who sponsored the program, and of course Cornwall Manor for allowing us back in to use this wonderful space. So please join us for our next lecture on Tuesday, April 11th, 2023. We'll be back in this room and also virtually when Mike Weber will return to tell us about the lost decade mining at Cornwall in the 1920s. Also, I invite you to please join us in person on Saturday, May 6th for the museum's cast iron cooking event. And just a reminder that the museum is open Friday through Sunday for tours. Please check our website for details about tour information. Another thing I'll ask you to do, we do have some free publications up front here, some of our Pennsylvania Heritage magazines. and also brochures for Cornwall Iron Furnace. So if you're interested and want a little bit of reading material, different information, that's free for the taking. However, what's not free for the taking is Mike's specimens of slag and his books here in the back. But Mike brought these different specimens up here, so if you want to, get hands-on and look at some of these different pieces, he has them laid out here and can explain a little bit about those. So again, I do really thank you all for coming out. You've been a wonderful audience. It's been 3 long years, so thank you for coming out. We at first were joking. It's like, well, it might be the 4 of us in this empty room talking to people online. And just to let you know, we had about 88 people join us virtually, as well as what we had in this room. So thank you very much. This has been a really great night. People got to hear a wonderful presentation. And of course, in a few days, we'll have this edited and up on our YouTube channel. So thank you very much and have a good night.